Hello, thank you very much for the introduction. So yes, my name is Cobee, and I'll be speaking about composite part design and manufacture for F1 racing. These principles are going to be quite top level, and if there's any questions about more details, then you can ask me afterwards. So
just a sec. Things happen. Don't worry, Paul. Take a breather. It's going to be okay.
I'll rehearse in my head.
Very good, very good. Let's try it again.
So, name is Cobee, composite part manufacturer in F1 and other motorsport applications. So, who am I?
Good.
I've been a composite design engineer in Formula 1 since 2017. Now, this isn't a very long time, but in the world of F1, where development happens very fast, that means that I've seen a whole range of regulations, and yeah, over my time, I've kind of seen it all. So I've worked on a quite wide variety of projects. So I've worked on parts such as the chassis, suspension carrier, impact structures, bodywork, wings, and floor, as well as many others. I've worked on basically every part of the car, apart from suspension legs and brake ducts. And again, the details that I am including in this presentation will be very top level, will not be specific to Alpine racing, and will be common to all F1 teams and most other motorsport applications. So to start off, what are CFRPs? Now, Robert kind of beat me to that one. But to answer that question, I have to first say, what are composites? Composites are a combination of two or more materials with different properties that enhance each other's properties to have a new set of physical properties. CFRPs, carbon fiber reinforced polymers, are the most common types of composite materials used on an F1 car. They compose over 80% of an F1 car by mass and over 90% by volume. So as I said, most common material type. These are woven or unidirectional sheets or plies of carbon fibers that are encased in a resin system to bind sheets together and enhance their properties. And these are hand-laminated plies by highly trained technicians into molds of various types. I will go into more detail in this presentation. So why do we use CFRPs over more conventional materials like machine metallics, plastics, or additive manufacturing? Well, to answer this question, I first need to explain what are the main performance drivers in material selection. So in Formula 1, everything is about reducing lap time. And to reduce lap time, the two main drivers are lightweightness, so we need a material that's as light as possible for the volume that we need, and extremely stiff materials that will conform to the aero profiles that are governed by the aero department at very elevated speeds. So this means that even though carbon fiber materials have very good properties and are dominant in a lot of different areas, the main areas that we use them for are their high specific strength and stiffness that allow us to have very thin panels that are extremely stiff when compared to other materials. Extremely good geometric freedom, which allows the aero department to have creative freedom within the regulations that are given to us, as well as easy to control properties, where different types of materials and different types of resin systems, different laminate structures and different interior materials can drastically change the behavior and the operation of a composite part. So what are the main drawbacks? Any material has drawbacks when compared to other materials. However, unfortunately, carbon fiber has quite a few. First of all, these are very expensive materials to manufacture and require highly trained labor. So a chassis, for example, a monocoque chassis for an F1 car will cost in the vicinity of about £1 million or euros. And that's for a single chassis that includes the labor cost, that includes laminate materials, machining time, and anything involved. So obviously not suitable for most automotive industries. These also have long project lead times when compared to other types of materials used. Now, this is obviously relative, so machined or additive parts will typically have a project lead time in the space of weeks between initial consumption and final part creation, whereas composites tend to be in the scope of months, which is still not very long. These are also not adequate in certain applications around the car, which include thermal applications and require thermal protection, hydraulic applications, abrasion and impact, and not related to Formula One specifically, medical and other environmental uses, where the toxic resin systems and the short fibers can be quite damaging. Another drawback is the anisotropic properties of carbon fibers when compared to other materials, which means that in different directions of tension, compression, and other loads, they do tend to not behave uniformly. And this means that it's quite difficult to predict the behavior of the part on the car, and typically slightly higher safety factors are used for the design of these when compared to more conventional methods. There's also an environmental impact to carbon fibers, which is quite predominant, and I will go into more detail about that at the end of the presentation. So, there are three main types of parts that are used in the world of F1, and that composite materials make up. First of all, there's the structural applications. These include the monocoque chassis, the impact structures, and the suspension carriers. These typically have reasonably simple geometry relative to other projects, but have very complex and very detailed laminate structures due to their high requirement for energy absorption, crash loads, and anything else. And they are homologated, so they do require much higher lead time than other projects. A chassis, for example, will take 12 months of development year by year. A suspension carrier will take 6 months, and impact structures tend to be around 3 months. We then have aero components, which are a lot more simple in terms of laminate structure, but will have much more complex geometry that varies a lot. These include wings, vanes, bodyworks, and louvers. And these, again, are quite simple laminate-wise, but have very quick turnaround in the order of 1 or 2 months for the more complex parts. And finally, integration-related parts, where the actual performance drivers are quite different, where we prioritize thermal performance, overall part quality, and tolerancing over others. And that means that these have very simple laminates, reasonably simple tooling, and do have a project lead time of just a few weeks. Now, composite materials, a lot of you will be familiar with carbon fibers in its most common form, the woven sheets, which are in the top right in the image. These are a very common type of material that is used in high-end automotive, in sports, and many other applications. But there are a lot of other types of carbon fibers, not only used in F1, but in general. These include spread toe, which are much thinner sheets, always within 0.1 of a mil thickness, and these allow for much finer granular adjustment of the properties of the structure. Unidirectional laminates, which are single unidirectional strands of carbon all aligned in the same direction and allow for very specific, very efficient load pathing inside composite structures. And finally, 5-harness and other fiber type configurations that allow for either compromises or much different types of properties. Carbon fibers aren't the actual only composite type of material in Formula One cars. The other types of composites include Kevlar and glass fiber composites, which have a whole new set of properties that help with abrasion, electrical interference reduction, and anything else, because carbon has quite high electrical interference, and for sensors, that's obviously quite a bad point. Now, internal materials. So most composite parts across the car aren't just a composite skin, because these tend to be under a millimeter thick, and have reasonably poor bending stiffness solely due to the thickness. This is why we tend to employ internal materials to either fill voids and create an increase in thickness, or provide rigid mounting points or higher stiffness characteristics for the overall structure. So these can be split into 2 categories. There's the lightweight reinforcements and the solid inserts. To start off, foam core is one of the more common types of internal reinforcement that is used. These are extremely lightweight. We're talking about 1/100th of the density of titanium or steel. These are very compressible and provide very good bending stiffness to the final part. These are typically used in vanes and wings to fill the gap between the 2 skins and provide good bending stiffness. Then we have honeycomb sheets, which are made of aramid or aluminium. These will typically be used in impact structure, as they will help with the bending stiffness of the final parts and improve the crash characteristics and any energy absorption details that are required by the FIA for driver safety. Next is solid inserts. A lot of the inserts that we use around the car are carbon inserts. So these are machined two-dimensional sheets of carbon, kind of like what Robert introduced in his presentation. These are applicable for medium structural requirements with directional constraints, and provides semi-rigid mounting points between different components. Then we have metal inserts, which will have much higher structural requirements. So these will be aluminum, titanium, or steel. They will provide much stronger mounting points, typically used for suspension or between large wings, like rear wings and front wings. And rapid prototypes or additive manufactured solid inserts, which will typically be used for lightweight fasteners around the car for bodywork and such. So moving along, I'd like to kind of give a global overview of how to manufacture a composite part for those not familiar. So one aspect that has to be kept in mind when manufacturing a composite part is the coefficient of thermal expansion. Because composite parts have to be cured in order for the resin system to bind the sheets together, these elevated temperatures can cause deformities in certain mold types. So we tend to use carbon fiber tooling to match the coefficient of thermal expansion of the actual finished parts. This in turn means that we need machined patterns that will have the global shape that we will need. We will then laminate and cure tooling on top of those patterns and inspect them individually and as an assembly to make sure that they will match our final part that we're looking for. We can then start the final part, and as I said, these will have complex laminates with internal structures. So these are typically comprised of two skins, one either side, and an internal structure built on solid inserts and lightweight materials on the inside. So the first step would be to laminate and debulk the actual skins, the fiber plies, onto their respective molds. We'll then prepare and assemble internals, so the foam cores and the inserts, and this is where we can use a lot of different really interesting advanced composite techniques, such as spars, bootlace, capping plies, and local patches to improve the overall characteristics of the part. We will then assemble the molds around these inserts and wrap the plies around and create a final part within the mold. We will cure as detailed, depending on the temperature requirements. And finally, we will inspect the cured part visually. Now, on an F1 car, most parts that come out of the molds are not yet ready for use. This means that the final part, in order to get it into this final stage for the car, will need to be trimmed and drilled as instructed from the mold. This is with the use of drill bushes and local details in the molds. We will also provide a series of jigs to bond, drill, trim, and do anything required to the final parts to get it ready for the car. And finally, we will inspect it as required, and this can be a certain number of factors that includes regulations from the FIA or internal requirements for conformity or anything like that. And potentially, for some more complex structures, we will have internal validation. Now, these parts now will make up bigger assemblies, and even within the assemblies, we have a number of choices. So the three main choices of assemblies that we can have are bolted assemblies, bonded assemblies, and one-piece parts. These don't seem very different, and you might think, who cares? But there are quite big differences between those. Bolted assemblies, for example, provide aeromodularity. If the aero department decides that they want to use a different type of flank or a different type of wing or something, they want to be able to substitute it in and have the part available. And yeah, it just allows for better testing. These also allow easier repairs and replacements between components. Parallel production of different parts, meaning that if you have more manpower, you can finish a project a lot quicker. And finally, unfortunately, these are heavier because they do include more solid inserts for mounting points and more fasteners. And as I detailed previously, the weight of the part is one of the main driving factors of performance. These are, the bonded assemblies, however, are lighter and stronger than bolted, as they are bonded with a much stronger agent. They ensure better fitments and better surface quality, as all the panels can be blended in together. However, these are a lot more difficult to swap parts between different aero configurations, as the part needs to be disbonded and rebonded. And finally, a one-piece parts, so a single laminated big part will be the lightest option, because there is no need for flanges, fasteners, or anything like that, or solid inserts. However, these are much more difficult to model and manufacture due to their larger nature and complexity. They provide no modularity for the aerodynamic departments to test out different options. And they are cheaper and quicker to manufacture as it's a single parts. However, they have to be done in series, so there's no scope for reducing the actual lead time of these parts. A good example of bolted assemblies will include the overall bodywork of the car, will include floor options that are adjusted quite regularly, and others. Bonded assemblies will include things like wings with flap elements that won't be swapped between races and between aerospecs. And finally, one-piece parts will be homologated structures and safety structures, like the chassis, impact structure, and suspension carrier. I've rambled on quite a bit about composite part manufacture, and I'm sorry if that was a lot of information, but I'd quickly like to explain the typical project development lifecycle for a standard parts, like a wing, for example. So firstly, an aero surface will be provided by the aero department that will fit within the regulations that are given to us and fit within the design scope that they have. This will be what they want to see on the car and how they would like to perform. We will then, the design office will provide approval and feedback for these shapes, say whether or not we are actually able to manufacture them as they want. And once given approval, we can get to the initial scheming of the part. This will include a very top-level detail of the internal structures and the laminate structures required, which will then be handed off to the stress department, which will use a number of tools like finite element analysis and other packages to sign off on the laminate structure as well as the internal structure. Once this is approved and defined, we can move on to final part design. This includes any detail required and the tooling and internal design, which further develops the details in the part. Once everything is finished on the design side, we then move on to manufacturing, where a team of skilled technicians will take our design and make it a reality. We'll then move on to validation, which again, most big assemblies like wings, impact structures, will have to be validated to meet F1 criteria. And finally, we can bring them to test, ensure that they conform to what we need, and we can race them. And hopefully bring the performance that the cost warrants. So, repairs. This is the less fun part of F1 for us. Naturally, F1 is a motorsport, so that does mean that we will see crashes and we will see impacts. Now, composite materials are very resistant to these types of impacts. However, due to the long lead time and cost for parts, this means that it can be quite expensive and time-consuming to get a new part to track. Now, this means that we will have to repair these in situ, and we have various methods for that. First of all, the inspection methods for composites include NDT, that Robert introduced in his presentation, that I won't go into. Visual inspections by the technicians and the mechanics that will be able to tell whether a part has a defect. And mechanical load testing, so we will apply design loads to the part and test whether they can still conform to their use case. If a defect is seen and reported, we have several methods for repairs within these. These include wet lamp patches, which are dry carbon or resin-impregnated carbon that will locally reinforce an area that's weakened. We have glue injection, which will fill any voids or any resin-weak or resin-dry areas. And finally, cut and shuts that will repair and fill any pulled-out inserts or any deformities in the final parts. Finally, as I said before, I would like to touch on some areas of research. one of the main issues with carbon fiber composites is the recycling methods. Now, as it stands, the current best method for recycling carbon fiber materials is pyrolysis. Pyrolysis is a high energy demanding process that is extremely expensive and not sustainable, which separates the toxic resins from cut, short fibers that will then be used in several applications. However, these short fibers lose the immense properties of carbon fibers due to their chopped nature and random orientation. So a lot of research has gone into methods for recycling these and using them for good purposes. One example of this is forged carbon fiber, like the part that I've shown. These are used in high-end automotive and some sports applications for their high mechanical properties, but also for their visual factor, which I think we can all agree is quite nice. There's also carbon-reinforced rapid prototyping, or additive manufacturing, which has become very prominent in the world, which is including chopped fibers or microfibers in 3D printed applications, and that can improve their properties quite drastically. Carbon mite is quite a common application for this, and there's actually been some companies like 9T Labs, who in 2021 have managed to find a way to integrate continuous fibers that are encased into the laminate in whatever orientation necessary, and that can increase the specific applications for composites massively. And these can be used for high volume applications, so this may potentially revolutionize the world of manufacturing. And the final topic I want to discuss on research is discontinuous fiber alignment deposition, which is something that I have personally worked on. And it is just additive manufacturing, but aligning fibers within the additive structure in order to yield specific properties and directional stiffness. Thank you very much for your time, and I'll be looking forward to your questions.
Thank you, Paul. Yes.